Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. Thanks for coming. It's an absolute pleasure to introduce George Klein. He's originally from Austria and got his PhD working with Tom Drummond in Cambridge, and he finished that in 2006. And he's currently a postdoc in Oxford, working with David Murray in the Active Vision Group. And I think I can promise you will see some absolute cutting-edge work on handheld simultaneous localization and mapping aimed at augmented reality. So take it away, George.
Well, thanks very much. Thanks, David, for inviting me here. It's a pleasure to be here. Keyframe-based SLAM for handheld AR. SLAM being simultaneous localization and mapping, and AR being augmented reality, which is actually what I've been really interested in for the last 5 or 6 years. Quick outline of the talk. Initially, I'm going to talk a bit about what augmented reality is and what we need for it. Then I'll see what previous attempts at visual SLAM relating to AR have been. And finally, I'll show how I think if we use keyframe-based SLAM, we can make a positive difference there. And finally, I'll show you some recent work we showed at ECCV, which is then making this keyframe-based SLAM more agile, specifically for handheld use. And the work I'm going to cover is from 2 papers. One of them is an ISMAR paper last year, and the other one this year's ECCV paper. So, augmented reality is inserting virtual graphics into the real world. This is pretty much what you get in the effect we'd like to achieve is the same as in movies, where you have really nicely rendered computer graphics which look like they're part of the real world, except we want to do this stuff live in real time on small devices as opposed to in a render farm taking weeks. It has a huge number of applications, and AR has sort of changed recently. We used to believe that this was the dream AR setup for everybody. Everybody would sport these very fashionable eyeglasses which would directly project the virtual graphics into the real world. Unfortunately, that hasn't really materialized. So now we're shifting to actually handheld AR using some sort of screen. So the setup I use is just a laptop with a camera, but increasingly we're looking at things like PDAs, and mobile phones are becoming powerful enough to be really the AR platform of choice. Now, fundamental requirement for providing augmented reality is registration. That means knowing where the camera is, or better said, where the viewer is relative to the world. For video see-through augmented reality, like I'm going to be talking about, that equates to just knowing where the camera is. So we need to track in real time the 6-DoF camera pose. The predominant approach in AR right now is to use, in fact, this here. This is the most cited paper in augmented reality for good reason, because it works and it works really well. This is Cato and Billinghurst's AR toolkit system. You print out these square fiducials, you put them around the scene. Your camera observes them, and it can work out, because they're quite distinctive, the pose of them, and it can work out the ID from the little pattern in the middle. And then you can draw your virtual graphics correctly registered in the scene. Now, there's some labs which actually go and print out dozens of these and put them all around the wall, so you can go anywhere in the lab and know where you are. Another application is you can actually move them around and have sort of interactions based on where these things are relative to each other. Now, so that's, if you can put fiducials around the scene, that's great. Otherwise, maybe we don't want to do that, but maybe we know a bit about the scene. So another approach to tracking in AR is to use models. So actually some work I did previously was we wanted to have this printer maintenance demo. So I measured out the edges of the printer, stuck them in a CAD file, and then we can track this by tracking these edges. A similar approach using feature points by EPFL, both circa 2003. And in general, if you have some sort of prior knowledge of the scene you're going to be trying to augment, then it makes a whole lot of sense to actually use this, because, well, then you can put your graphics in the right place and tracking works great and everything's fine. But today, we're looking at something a bit more tricky. We're looking at the situation where you don't have any prior information about the scene, where you essentially have to learn the structure of the scene at the same time as learning the camera motion. And this problem is well studied as SLAM in the robotics community. So they're really interested in a robot like the one we have here, exploring the world and figuring out the structure of the world it's exploring at the same time as working out where it is. And big topic in robotics, mostly using a wide array of sensors. For example, laser rangefinders, as you can see mounted on this robot here, 2 of them, which give you both an orientation and a range of a sort of sweep of laser across the room. In computer vision, SLAM is a bit less well established. It's the first real-time monocular SLAM system was actually presented by Davison in 2003. Ever since, there's been a bit of interest. So looking at a few developments, like I said, initial EKF SLAM implementation 2003 by Andrew Davison. Then we had a UKF implementation, which was a bit more robust thanks to using SIF descriptors. Finally, Eden Drummond started doing interesting work using different type of filtering frameworks. So FastSLAM 2, which can handle many more features. And finally, something called Local SLAM, which is a combination of using EKFs and bundle adjustments to tie local submaps together. But all of these have something in common. They're all filtering methods. And there has been application of these methods to AR. I'll just show you some of these. Davison presented way back in 2004 this kitchen augmentation software using a SLAM system. Then we actually tried doing some work bringing SLAM to AR in 2007. Likewise, a few attempts at ISMAR. Let me just show you what this looked like here. This was the first application of real-time EKF SLAM to AR by Nick Moulton, Andrew Davison, and Voltaire Mail. Let me just forward a bit. This is perhaps, if you're not familiar with the sort of EKF SLAM history and vision, this is a pretty early system. Essentially, you move the camera around and features are added to the map, and it can work out where the camera is from that. And eventually, if we fast forward, here you can see the map being created as the camera is moving around. If we fast forward a bit, you'll see then here a shelf has been added to the map, and this is now integrated into the scene as augmented reality. So just to show you our efforts in this direction, the focus of this work was actually to add a relocalizer to SLAM. Because SLAM occasionally broke, we needed a method to recover from tracking failure. So we had this demo here where we put these circles in the world and then a little guy ran in between them. And the idea is that this is correctly integrated into the world. Now, slight problem though, you'll see perhaps these, if I just rewind a bit, everything's sort of not quite completely stable. Everything sort of jitters around a bit. The quality of tracking isn't really that great. And we ended up encountering some other issues. And in general, the frame-to-frame SLAM methods we saw applied to AR were all somewhat fragile. So first of all, starting with this tracking jitter I just showed you, this is partially due to the fact that all these...
Can you say a little bit more about what you mean by frame and what do you mean by filtering? You just say these are all of these methods just use filtering, and I don't...
I'll have a slide on that in just a second. Yeah. But please do, if you have questions, do please ask right away. Well, there's a number of reasons, I think. First of all, the maps are all relatively sparse, so there's not many features. This contributes to the jittery tracking. There's agile motion. As soon as we move the camera fast, most of these SLAM methods will fail. And finally, certainly in the methods we used, after a long-term exploration of the environment, eventually the map always ends up corrupt, and that makes the whole system fail. And to look at why this is, explaining now what I mean by frame SLAM, all these systems work by filtering a certain estimate of the state. And this state vector includes, I've given an example down here for the case of EKF SLAM. We're estimating the camera pose up here, and also camera velocity. And simultaneously, all these y's here, these are all the point features which make up the map. So we have maybe a camera pose and say 100 feature points in the world, and we're estimating jointly the position of the camera and the position of all these feature points. And every frame, we're going to make some measurements and then filter these into this distribution over this feature vector here. In the case of EKF SLAM, the distribution is described just by a single Gaussian PDF. Staying with the example of PDF SLAM, this is what you do every frame. First, you modify the state vector by applying some sort of motion model and process noise, which also expands your uncertainty. Then you project your current uncertainty of the feature vector into the image. This is the principle of Andrew Davison's active search. You can see here it's drawn all these ellipses. These are the projections of the Gaussian state estimate into the current frame. Using these ellipses, we can then make some measurements by localizing within each search ellipse the appropriate feature. And then we can take these measurements and use them to modify our state and reduce our uncertainty, integrate them into our current state estimate. Finally, the measurements, once we've done that, we've got our new updated posterior state estimate for that frame, and then the measurements are discarded. So I hope that answered your question. Good. There's a couple of downsides to this approach. So the first two are perhaps not fundamental, but there's certainly currently a downside. The first is scalability. So you're filtering a huge state vector here, your whole map and also camera pose. And this turns out to be quite expensive if you want to do this every frame. You need to do this at 30 Hertz to provide good graphics for AR. And this then favors reducing the size of the state vector by, say, running with a small map. So, for example, Andrew Davison has the phrase of using a sparse map of high-quality features. Essentially, the idea is almost to use as few features as you can to ensure proper localization of the camera. Another problem is currently consistency. This is a property of monocular SLAM systems due to unfortunate mathematical reasons, to overestimate the amount of information they have. This means that their uncertainty estimate ends up too small, which leads to corruption of the map. Now, this might not be a fundamental problem, but it's certainly a problem which all current methods have, unfortunately. But the biggest downside to frame-to-frame SLAM and this filtering approach is what happens if one of your measurements was incorrect. Now, these measurements, they go into the PDF, and then they're locked in. You can never get them out again. So that means if you make a single incorrect measurement at any time in any frame, you've actually permanently corrupted your map. Now, this is a big enough problem that current SLAM implementations go through a great deal of effort to ever avoid this from happening. So we start with even the active search I showed you first. This projecting the ellipse into the image helps not only concentrate the processing on the regions where it's most useful, which helps real-time operation, but it also means that we're not going to get any outliers because we're not going to look into unlikely regions. Also, there's various binary methods for trying to avoid including outliers. So there's joint compatibility, branch and bound, or ransack. Both of those do roughly the same thing. Split all the measurements into an inlier set and an outlier set. And finally, most SLAM systems require some sort of conservative tuning. You really want to avoid including outliers, so you have to maybe shrink the size of your search ellipses. And all this essentially prevents agile operation. So this is our proposed alternative, keyframe-based SLAM. We don't want to have this effect where we discard measurements and have them corrupt our map. So we're going to keep all our measurements and essentially do all of our estimation using bundle adjustment. So instead of filtering, we use bundle adjustment. We keep all the measurements we ever make which go into the map. And also, we keep all the poses in the bundle adjustment, which means that the whole thing, estimating all the poses and all the map points using bundle adjustment is pretty much the optimal way of determining camera trajectory and map structure from a bunch of monocular measurements. Unfortunately, this is we can't possibly do this at 30 Hertz. We can't keep all the frames we've ever seen and all the poses and try and update this every frame at 30 Hertz, given that bundle adjustment eventually will scale as the cube of the number of poses in the estimation. So what we're going to do is we're going to keep a subset of our poses. We're going to call these keyframes. And once we've done that, once we've decided we're not going to use every frame, we can actually split off the mapping component from the tracking and run the two in separate threads, which, given that now everybody has dual-core machines, we can run them in parallel on the same processor, run mapping and tracking. So here are these two threads. On the one hand, we have a tracking thread. This is responsible for estimating the camera pose so that we can get our nice augmented graphics in the right place. This, therefore, has to run at 30 Hertz, but it can simplify that by assuming that the map is fixed, which means that all it ever has to estimate is 6 degree of freedom camera pose. Then we can focus on making this thread as, we can try and make the tracking as good as it can possibly be, given the map. So we're going to focus on robustness, agility, and also try and get it as accurate as possible. On the other side, we have the mapping thread, which is trying to make the map. And this, since we're not looking at every frame, we can actually take our time for every keyframe. We can spend lots of time and try and make the map really as good as it can be, given the keyframes it has to work with. There's a bit of interaction between the two. The mapping thread obviously provides the map for the tracking thread, and the tracking thread occasionally gives keyframes to the mapping thread. So let's look initially at how we make the map. The map, as usual in SLAM systems, is a cloud of point features. It's made from the set of keyframes, which means the whole thing is actually quite similar to multi-view reconstruction techniques, except that we don't start with all the keyframes ab initio. We start with a single stereo pair, and then keyframes are added as the system goes along. All the keyframes that we add usually have a pose already attached to them because they came from the tracking system, which calculates this pose, except for the first two. And here we have to do something special, and this is just a stereo initialization. So here you can use any stereo algorithm you'd like. We used to use 5-point pose. Now, because we usually run on scenes which include a planar target, we've used a homography initializer instead. So you just, all this needs is a stereo pair with feature matches between them. The way we generate these feature matches is we need cooperation from the user. So we have the user place the camera, press a button, move the camera gently, and press another button. It can track the features between these two frames and generate an initial stereo pair from that.
Question about that. There's this ambiguity, right? If you have a plane and two cameras.
Yes.
So you avoid that by choosing a decent pair that's not.
Yes, and it's also, the scene is never quite planar. There's, once the stereo pair is created, then the mapping thread enters this here infinite loop, whereby it's essentially idle until it gets a new keyframe. When it gets a new keyframe, it then starts adding new points, integrates that keyframe into the whole estimation. Once it's added new points, it goes and optimizes the map using bundle adjustment. And finally, it does a bit of map maintenance and perhaps iterates over this if the bundle adjustment didn't quite converge. So I'll now go over these steps and explain them. So keyframes, we don't want every frame to be a keyframe. We only want a keyframe if A, it's not in exactly the same place as or any of the other keyframes already were. We need some sort of baseline in order to add and triangulate features. So we want a certain separation between a new keyframe and all the other previous ones. We also want the frame to be good. And that means it shouldn't be motion blurred, so we can add features well. And finally, the tracking should actually be reasonably confident of the position estimate it had for that keyframe. Then when a keyframe is added, if the mapping thread was doing anything like a huge big bundle adjustment, all that gets stopped, and it handles a new keyframe as a priority. It tries to add new points to the map, and even before it does that, it tries to measure all the points which are already in the map in that keyframe just to get as much information out of it as possible. So to add new points to the map, this is one of the key places where our system differs from other SLAM systems. We want our maps to be as rich as possible, which means that everything in the keyframe which can be a map point, it will try to make a map point. So it'll go and do we take all the maximal fast corners in the keyframe. We first check if there's already a map point there. If there is, then skip it. Otherwise, it'll then do a Shitomase score check just to see if there's enough gradient information there. And if it isn't already in a map, then this will be attempted to add as a map point to the map. The way that happens is we extract an 8x8 pixel patch, and then we try and find the same patch in a neighboring keyframe by epipolar search. If we can find it, then we triangulate it, add it to the map, and we repeat this 4 times. We work not only on the full-size image, which is 640 by 480. We also go through 3 other pyramid levels, shrinking the image by half every time. This lets us later do some coarse-defined tracking and also lets us track across multiple scales as the camera changes distance from the target. bundle adjustment looks like this. What we're doing is we're optimizing all of the keyframe poses except for the first, and all of the map's point positions to minimize the reprojection error of all the measurements we've ever made in any keyframe. We use a robust estimator for the reprojection error. We use the 2-key estimator for that. This has the advantage that outliers are flagged, and we can then remove outlier measurements from the estimation at a later date. This is implemented as a Levenberg markout solver, and it scales. Ultimately, if we had many, many keyframes, it would scale cubically with the number of keyframes. In practice, we find, much as you have, that it scales quadratically with the number of views.
Are you handling the camera sparsity of this? Because I suppose you have a straight line, you move along a long street, it shouldn't be cubed if you handle it fully.
Right. Well, no, I just project the map points onto the cameras, but beyond that, I don't do anything else. So I don't do any variable reordering or, and in practice, if I move around like this, it will probably turn out that pretty much every view can see every point. But yes, this is expensive. So this can take tens of seconds to converge as we hit our sort of scalability limit of, say, about 200 keyframes. This means if I'm exploring, I don't want to wait tens of seconds for each new keyframe to be added. As I said earlier, we can actually abort this if a new keyframe is coming along, but we also do something else. When we're exploring, we do a local bundle adjustment initially, which is just a bundle adjustment of a few local keyframes individually. And then once that's converged, we can then go and bundle adjust the entire map. Then finally, once bundle adjustment has converged and the map maker is just sitting there waiting for a new keyframe, it has a bit of idle time. So it can do a bit of housekeeping. There's several things it does. First of all, if there was ever a measurement in the bundle adjustment that was flagged as an error, it'll go back and try and search in that keyframe again, because we keep all the keyframes, see if it can make a better measurement of that point. Likewise, new features which are added to the map, we seek them out in all the old keyframes and see if we can maybe make measurements of them there. In general, we try and make the map as dense as possible to fill in as much information as possible, which is actually pretty much the opposite of what you'd maybe want to do if you were trying to explore with a robot. So that covers the operation of the mapping thread. I'll now tell you what the tracker does. This is reasonably straightforward. It just tries to track at 30 hertz to provide camera pose for augmented reality. We want it to be 30 hertz, accurate. So that means low jitter, and also we want good absolute accuracy. Would like it to be reasonably robust to temporary occlusions, things like people's hands moving in front of it. And it should ideally support the user moving the camera in a fairly unconstrained manner. We don't want to have to treat this camera as a sort of raw egg. And we can now do that because we've separated the tracker from the map making. We can do all sorts of mistakes in tracking, and they won't immediately corrupt the map, which means we can be quite aggressive. We assume that the map is fixed. There's no estimate of uncertainty in any of the map positions. And we use the standard active search method. So we project the features into the image, find matches in a circle around the projection, and then update the camera pose to minimize this reprojection error. We're going to do 2 stages of tracking, a coarse-to-fine method. So initially we try and project the coarsest points into the image, then find them, estimate the sort of intermediate camera pose, and then use that to find many more measurements and get our final camera pose estimate. Once we've done the fine stage, then we have a quality assessment. Finally, we can draw the augmented graphics in the correct place. So initially, frame comes in, we pre-process it, we split it into a black and white version, which we use for tracking, and a color version, which we use for augmented reality. We generate our pyramid levels from 640/480 all the way to 80 by 60, and detect fast corners in each of these. So this whole pre-processing is fairly rapid. It takes 3 milliseconds, and now we can go and project our features into the image and try and find them. To project the points, first we take our previous frame estimate and apply a decaying camera velocity model. And then we might have 10,000 or 20,000 points in our map. We project all of these into the current viewing frustum and keep maybe the few thousand which we can possibly see in the current view. Then we also filter them according to how big they are. If they're way too big compared to where we first saw them, we discard them. Otherwise, if the patch normal is pointing in the wrong direction, we discard them. And we'll maybe end up with 2,000 or 3,000, which we might be able to measure that frame. We can't measure all of them at 30 hertz, so we restrict ourselves to measuring only 1,000 of them. Initially, we choose the biggest 50, the ones which will be most likely to be found even despite big camera motion. Search for them, do a pose update, and then search for 1,000 of the smaller ones. The way the patches are found is we use 8x8 pixel patches. This is very fast, although the quality is not so great. We generate the search template by warping them according to our estimate of the patch's patch normal. And then we project them into the image and search in a fixed circle around the projection using zero mean SSD, restricting our search to fast corners. This makes it possible to search for so many features. If we tried to exhaustively search all these circles, we couldn't possibly handle this many points. And finally, we find each point to sub-pixel accuracy using some Lucas-Canade tracking once we already have the pixel-precise estimate from the search. Then finally, updating camera pose is just a minimization in 6 degrees of freedom. Again, we use a 2-key estimator, and this iterates 10 times per frame. So finally, the tracking quality. This is our protection of the map from the poor estimates of the tracker, as it were. We want to only include good keyframes in the map, which means that if the tracker is going a bit crazy, we don't want to use those as keyframes. What we have for this is a number of heuristics. So first of all, we want to limit frames by the amount of motion blur in them. Because if we put motion blurred frames into the keyframe, this will break. Well, we won't be able to add many new features from that frame. We also won't be able to find any new features from other frames. So we essentially don't want these frames. Also, we just have a check, which is based on the number of features the tracker can find compared to the number of features the tracker wants to find, just to see if the tracker thinks this is a good frame estimate. Also, if the tracking performance is really poor, then we just declare a tracking lost and we initialize a recovery process, which I'll talk about at the end. So let me just show you what I've talked about so far. So starting with the stereo initialization procedure. So what I'm going to do is I'm going to hold the camera here, press a button, and then you can see all these little, these are my feature correspondences for the first stereo frame. The second time I press the button, it'll have generated a very simple 3D map of the initial plane that it saw. You can also see a sort of cloud of outliers down here. And then as I move the camera around, it's, whenever I get sufficiently far from previous keyframes, you can see it inserts a keyframe, and as it does so, it'll add new points to the map. So as I move the camera around, it'll hopefully start adding a few features, occasionally breaking. And then in this way, I can grow the map. Now, this is this here represents roughly what our system looked like this time last year. And this still had, you can see the map here. You can see just now I've generated a map. This has 22 keyframes and 1,600 point features. As I move around, I can maybe add a few more. And as you can see, the map contains not only inliers, but also a huge number of outliers. So down here, for example, this was features which were aliased from the keyboard because it's a repeating structure. It gets the second depth plane further down. Things like that don't really affect the operation of the system too badly. So this is due to the use of robust estimation throughout, not only in the tracking, but also in the map generation. So even if we do have bad measurements in the map, they don't end up affecting the quality of the thing too badly. But anyway, let me carry on. So already with just the points, we can, in a suitably textured environment, we can generate maps of many thousands of features, say up to 10 or 20,000 using up to 200 keyframes. And if we insert virtual graphics into this, then the quality of the tracking far exceeds that what we got from EKF. I'll show you more demos later, but let me just say that we still had a few problems at this stage. So although we could make these maps, the tracking quality wasn't perhaps as good as we would have liked. It's also, of course, we have the scalability issue. It doesn't go past 200 keyframes. The quality heuristics are poor. But the problem I'm going to talk about now is the agility, really. So as we start shaking the camera around, tracking will very frequently fail. And although we now have methods of recovering from tracking failure, this is still an annoyance for the user, and it'd be better if tracking didn't fail in the first place. Part of the reason tracking fails is the sort of cameras we use, quite small lenses, quite small sensors, don't really gather a huge amount of light, so they need to have very long exposure times, pretty much 30 milliseconds on this model. So we soon start running into images like this is like this. This is a standard image. If I move the camera a bit already, you can see a fairly substantial motion blur. And this is what happens if I start really shaking it around. And this is a problem for us. As I said earlier, we use the fast corner detector to find our features. On an image like this, the fast corner detector will only find image noise as corners and no actual true corners. Even if the fast corner detector did find corners, it probably actually would have trouble finding them with their 8x8 pixel search patch, because the 8x8 pixel patch is just going to be completely dominated by motion blur. So we need something to be able to track these sort of images, ideally. So we came up with something, two methods I'm going to talk about. One of them is to add edgelets to the map. And I'll tell you why in just a moment. And the other is to add a frame-to-frame rotation estimator, which becomes necessary when we add edgelets. So first of all, edgelets. Why? Well, here's an image of a kitchen and a canny edge extraction next to it. And you can see it's nicely populated by edges in every old orientation. And it looks actually really nice and trackable, that image. Now, edges have the property that they're locally one-dimensional. And actually, motion blur is too. So what happens if we motion blur this image is that we've lost all the vertical edges, except maybe there's one still left here. But all the horizontal edges are actually still there. We can still detect them with the standard edge detector, which means we should be able to track them trivially. So whereas most of the point features here have been wiped out, half of the edges are still there. Not only that, we can actually even track the ones which have been blurred. If there were nice, strong intensity steps, then a motion blur is just convolving that with the box filter, which produces, instead of an intensity step, an intensity ramp. So if instead of looking for an intensity step, we just look for an intensity ramp using matched filter, then we actually still get a reasonably strong response at the correct location. So we should be able to track these blurred edges. Now, people have tried tracking edges in SLAM systems before. There's been two notable previous approaches, both presented at the BMVC in 2006. They're very different. So the first was the system by Smith, Reed, and Davison, which was based fundamentally on EKF SLAM. EKF SLAM doesn't scale very gracefully with the number of map features. So the approach taken here was to include as few edges as possible, but to make these edges really good. So Paul Smith, he went and tried to find long edges in between corners. He looked at every pair of image corners in the image and checked if there was a long edge in between them. And if there was, they were added to the map. The other approach was that of Eden Drummond, who they didn't use the EKF, they used FastSlam 2 as the underlying SLAM engine. And this scales more gracefully with a number of map features. So they were able to not look for few long edges, but rather to add all these tiny little edgelets to the image, which has the advantage that if you're looking at a long edge, which is not all in the image at the same time, you can still track it by just adding all these little small features to it as you go along. So we used the method of Ethan Drummond, or better said, we used the concept of using edgelets. So an edgelet is this very small piece of an edge, which is only locally straight, and a long edge will be made of many, many, many of these. The way we present them is we give it the full 6 degree of freedom coordinate frame. So relative to the world, it has a full coordinate frame transformation such that the transition from dark to light is in the direction of its x-axis, and the edgelet itself points along the z-axis. Now, this is clearly an over-parameterization, given that this only has 4 degrees of freedom. But of course, we only optimize the relevant 4 degrees of freedom in the optimization. That means we ignore rotation around the z-axis and translation along the z-axis. To add new edges then to our SLAM system, well, it's much the same as how we add points. Whenever we add a new keyframe to the system, we find candidate edges in it. For this, we use a plain candy edge extractor with a slightly modified edge linker. And then we use epipolar search to add these edges to the map. So let me just go through this. This might be a new keyframe. We perform a maximal edgelet extraction, much like canny. And then when we link these things together, we slightly modify this so that it breaks the chains at points of high curvature. So we're left with these chains of locally reasonably straight edges. And then we walk along these chains and try and find things which actually qualify as edgelets in our measurement stage, which I'll describe later. These are all candidate edgelets. We're going to try and add these to the map, all of them again. And to do that, we perform epipolar search in another keyframe. And unfortunately, since edgelets are, well, they all look the same, we're going to get a lot of matches on each one. This means we have to go to a third keyframe and verify each hypothesis, and only add these to the map if we only get one correct hypothesis. So, having added the key edgelets to the map, we still need to do image measurements to actually then optimize them in bundle adjustment, and this will work much like edge trackers do. This is basically this is going to do the same as the rapid edge tracker from 1989. Initially, we project an edgelet into the image. Then we initialize sample points along it, and from each sample point do a perpendicular search into the image to find the nearest intensity, to find the nearest maximal gradient. Now this can be, because this is this is a keyframe measurement procedure. So remember, these keyframes are nicely behaved. They have no motion blur, and the tracker has a really good pose estimate already. So this search is going to be very, very local. It can be very constrained, and we try and make it as accurate as possible. So once we've done the search, we do a best fit straight line, and then this straight line becomes the measurement of that edgelet and that keyframe. And this is what you use to perform bundle adjustment. In bundle adjustment, we project the current estimate in, and then initialize these two virtual sample points against that best fit line. And this is our 2 degree of freedom measurement of an edgelet error in a keyframe. So let me show you. So here's that kitchen scene. This is just all the point features, and then as soon as we add edges, it's actually visually reasonably satisfying. You can suddenly see all this sort of structure emerge, and it's although we don't exploit this for a human operator yet, it does actually make a nice difference perceptually. So in the tracker, now the tracker's frames aren't nearly as nicely behaved as the ones the mapmaker encounters. So here we don't have any guarantees about no motion blur. The way we're going to track edges in the tracker is very different. First of all, in motion blur, there's really no point in trying to determine the angle of an edgelet, given how small they are and given how blurred the frame is going to be. So we're only going to make a 1 degree of freedom measurement, which is a perpendicular distance. We project the edgelet into the current frame, and then we look for the nearest, instead of intensity step, we now look for the nearest intensity ramp, as said earlier. And this will be based on an estimate of the camera's current rotational velocity. Finally, this would work perfectly if all image edges lived in isolation. Unfortunately, what happens in practice is that you get maybe an edge which is you get a switch from dark to light back to dark. So if you blur this, you'll find that these two edges will merge together, and in fact the position of the maximum will move. So we want to avoid taking these measurements because we'll no longer be measuring just a single edgelet. The way we avoid this is in each keyframe, we actually go to each edgelet and simulate what would happen in an edge search under certain levels of motion blur. And this tells us what the maximum search range we can use for any level of motion blur is, and also what sort of edge threshold we should set for the edgelet search later on. So, so much for edgelets. Let me just then talk about the rotation estimator. This will handle rapid accelerations. So the edgelets can track motion blur. Motion blur happens in rapid velocities. So now maybe we can track the rapid velocities, But we need to have an estimate of how fast the camera was rotating in order to predict how much motion blur there was so that we can track them. So velocities are okay, but accelerations are now going to be a problem. And for this, we add this frame-to-frame rotation estimator. What we do is we try and emulate the effect of having a gyroscope strapped to the camera. Most of the sort of rapid accelerations that happen in handheld motion are due to camera rotation rather than translation. So we're going to assume that the big image motions between frames are only due to rotation and try to estimate this between every frame. We do this by a direct 3-degree of freedom image-to-image minimization using, we subsample each image down to very low resolution, down to 40 by 30 pixels, so it looks like this. And then, just to aid convergence a bit, we add a bit more Gaussian blur. And then we essentially just track the 3-degree of freedom difference between these two frames. This usually converges in 5 or 6 iterations using efficient second-order minimization. And then we transform this 3-degree freedom image space transformation into a 3-degree freedom camera rotation by taking account of the camera parameters. And that's it. That gives us our frame-to-frame rotation estimate. This is very quick because the images are so small. This takes just half a millisecond to estimate. And yeah, that's
purely iterative from no motion, or do you actually do a search first?
No, start from no motion. Yeah, and it's no longer 10. It's now more like 6 iterations. There was a bug. So yeah, let me then show you what the result is. Sorry, I'm going to have to lock down the exposure otherwise. So now, if we look at the map, you can see, well, apart from a huge outlier, we can see apart from points, we also have these sort of glowing green edges being added. And you can see if I zoom into them, you can see initially the estimate might be reasonably poor, but as I add more and more measurements, they sort of end up straightening out and forming hopefully continuous long edges. Now, as it takes a bit longer to add the edgelets to the map than it does to add the map points because I need, for map points, any 2 views will do, because it'll give me a baseline. For edgelets, of course, if I move the camera vertically, I can only add horizontal edgelets. And if I move the camera horizontally, then I can add vertical edgelets. So it takes a bit more moving around to get lots of edges in the map. But eventually, I can hopefully add a reasonable number to the map and get a nicely filled-in scene. So then, yeah, these things basically help me track the camera reasonably fast. Let me just show you what the rotation estimator does. If I turn off tracking completely, right? If you just look at this grid here, this is sort of my initial reference plane I have. If I now turn off tracking entirely, now I'm just using the rotation estimator. You can see it pretty much follows the camera rotations around and is pretty immune to rapid things. Of course, translation will be misinterpreted as rotation. So we still need proper tracking. And also, it's quite sensitive to this sort of thing. You can see as I move my hand in front of it, because it's using the whole image at once, it can't tell that my hand isn't part of the scene. But combined with tracking and the edgelets, it then gives me a sort of reasonably agile performance. I can sort of move this thing around and dance around the scene quite a bit. And it'll happily handle reasonable amounts of motion blur. And I think it's probably best if you're curious that I let you have a play with it first, so that you can judge for yourselves how well this works or not.
I probably missed. Do you do this to one of the keyframes, like the best one, or is it frame to frame? I was wondering why it's not accumulating error when you're moving your hand in front of it.
Oh, that's just the frame to frame tracker.
It's frame to frame, but then I would think that you could somehow trick it by moving your hand off and get it permanently lost. But then it will recapture only when you do it again. Is that
Well, hopefully the tracking quality heuristics will will capture the fact that it had an error. So yes, I can get if I sort of wave my hand in front of it, if I turned all the tracking things off, then it would do this rotation. But of course, it's also tracking the features. And this happens after that estimator. So it's sort of it'll reasonably stay snapped on until it gets to a certain critical thing, and then it'll just break completely. But it'll recognize that it's broken and not at a keyframe, hopefully. But yes, this is a disadvantage of adding this estimator. For sort of general manipulation, as you might get in AR, it's usually not a problem. It's just this sort of thing used to be more robust before I added it. Right, so just to show a few more things. This was this kitchen thing I had earlier. And just in the videos, you can actually sort of pause during some of the frames. Here you can see, for example, reasonable quantities of motion blur. You can see this whole part of the image. It's completely wiped out all the point features here. These point features here are, in fact, incorrect. These are just image noise where it incorrectly made a measurement. And yet, all the features, all the edges that you can see drawn were actually tracked in this frame, and that's what's providing the camera pose estimate during these sorts of motions. To show another. This here is a graph of what happens to the number of features we can track as camera motion increases. You can see the points drop off quite quickly as we get a bit of motion blur, whereas edges, partially due to this directional nature, because some of them will always remain unblurred, we can still track them. Of course, it doesn't really help if we can only track the unblurred edges because they won't fully constrain the camera pose, but it does help somewhat. So, finally, let me talk quickly about how we recover from failure. This used to be a big deal for SLAM systems. They were basically unusable in practice because as soon as the tracking went even slightly wrong, you had to start from scratch. So a number of people started looking at recovering from tracking failure. One of our approaches was actually to use the map to recover. So this was joint work with Brian Williams and Ian Reed. What we did was we took our EKF SLAM thing and trained a randomized trees classifier for each map point. Then, when tracking was lost, we were able to generate correspondences from a novel view. So we could say, this point is the one we have in the map over there. And then using just ransack, you can estimate where the camera is in the map and restart tracking. Now, this has since there's been a number of other approaches along a similar vein since, mostly replacing the randomized trees with other forms of classifiers because randomized trees don't scale hugely well with number of feature points. So, for example, Ian and Drummond have a version of this which runs with SIFT and bags of words. Otherwise, Cheklov in Bristol had a Har wavelet pre-filter. And finally, there is actually a version of randomized trees which does scale to map points, which was presented at UCCB this year, and that's been used for SLAM relocalization as well. But all these methods are actually, they take quite a bit to implement. They also don't really exploit the fact that we have keyframes in our map. So what I tried instead was to actually, instead of relocalizing against the map of points, try relocalizing against the images of the keyframes instead. So this can actually be done trivially easily. What we do is, when we're lost, we as we're adding in new keyframes, we take each keyframe and we subsample it down to 40 by 30 pixels, and then we blur it very heavily. And this blurred image is actually going to be our descriptor for each keyframe. So we have all of our keyframes for a small scene here. This is just 100 keyframes. Then if the camera ever gets lost, all you do is you do the same procedure to the current view, and you just compare this to all the other keyframes in the map using zero mean SSD, and that'll actually remarkably usually give you the correct match. And then, of course, the camera won't be in exactly the same position, so you use the rotation estimator I described earlier to match the rotations. And even though it still won't be in the same translated position, this will now be close enough that the tracker can then lock on in the first frame and resume tracking. So, of course, this has huge problems. If I change the lighting substantially, this will fail. If I change the scene layout substantially, this will fail. It can't relocalize upside down, which we used to be able to do, but, well, that's no huge loss. It has a very nice property that it's extremely predictable in operation. Essentially, if you were tracking here and tracking worked fine, and then you move here and it breaks, all you have to do is move the camera somewhere where it was before, and then tracking resumes. And this often happens so fast that people won't even notice that tracking has failed. And it's also extremely quick. It takes 1.5 milliseconds for as big a map as we ever make. Right, well, so much for relocalization. That pretty much concludes my talk. Just a few things in conclusion. First of all, I quite like this idea of using keyframes. Many people think it's inelegant to not use all the information in estimating the map, but I just have the opinion that basically some frames are not worth using. It's a somewhat philosophical difference in computer vision. I think actually in practice you can't just use appropriate noise models for some of the bad measurements you get, and it's better to just throw some data away. So instead of looking at all frames and performing some sort of minimal processing spread out over everything, we just choose a few that we think are good, and we concentrate all of our processing resources on these. And I think this gets a better result. Then, the way we've split apart the tracking from the mapping is not very complex. We essentially just create the map on one process and read it out from the other. It turns out this is not at all a problem with things like synchronization. It really hasn't been an issue at all. And the split does allow us to make the tracking far, far more robust and aggressive than we could otherwise do it if the results from the tracking were always fed into the map-making stage. And finally, this method is very problem-specific. So I work with my camera in my hand in a small volume. I don't try and make large loops around buildings. But this is not in any way a replacement for general-purpose SLAM. It's just something that works quite well for the sort of augmented reality problems I try and deal with. All right, well, thank you very much.
Show us Darth Vader.
Oh, yes, of course. So I haven't actually showed you any of my AR games. So I said initially that I use this plane initializer. That's because, well, if you're going to do SLAM in an unknown environment, the big question is, what can you actually helpfully draw into this environment which makes sense? Well, not very much. But if we know that there's a plane in there, then we can start adding things to that plane. And so, for example, well, let me just get right to it. So this is the old favorite. Now I've got a little character running around my computer here. And eventually I'll get these little hordes of enemies here. And then you can sort of shoot them and do little things like this. Let me perhaps show some videos of this. So just because you've only seen the tracking in the same environment, this is actually where I do all of my work, my helpfully cluttered desk, showing lots of good structure for the system to use and build the maps. And this is sort of the intended scale of operation for the system. Now, if I forward a bit, you'll see here this is slightly different environments. This is just shot from a train window. As soon as there's anything planar in the environment like this, then we can actually go and augment it. And it'll be reasonably happy with that. Then, once again, start with a planar environment, and after that you can move around. The rest of the environment doesn't have to be planar. You can sort of expand it as you will. You can see here the large amounts of clutter outside. Back then didn't bother the system at all. I have to admit I haven't tried it now with the rotation estimator, but that might now make a difference. You'll soon see the map superimposed on the world here, which shows you all the features it's added to the world and carries on adding as the camera moves around. So another example from outdoors. You can see, even though it doesn't really have much texture on the ground, there's enough texture around it to actually constrain the camera pose fairly well. And again, you can run these little games of having characters run around.
Say you added audio, but it was way too annoying.
Yeah, this is just an example of tracking slightly larger environments. We don't have any explicit loop closing mechanism. So there's nothing there which actively recognizes when the camera's gone around a loop. But because we use bundle adjustment and sub-pixel measurements, it's actually accurate enough that you have a fairly good chance of the loop just closing itself, although that's by no means guaranteed. And then here we have some failure modes. This made more sense if you were in ISMAR. But first of all, we have very repeated texture on the ground, so this is going to track very poorly. And then you'll see the map actually gets substantially changed by this thing starting to move around, and that makes tracking very unhappy. Then again, there's some things we can't handle. We add features by epipolar search. If you look at this foliage here, everything looks like everything else. The epipolar search fails completely, and the repeated texture breaks tracking. Similar sort of thing here with the gravel ground, corner features everywhere. Everything looks much like everything else, and again, we just have way too many bad features for the system to handle. And finally, another little example of the sort of augmentations we can add to a planar scene. If we know that it's a plane, then we can lift the texture off and manipulate it and make it appear as if the environment is actually deforming. Right.
So the biggest problem in having it work over longer ranges is just closing the loop? I encounter a very different problem. It's dealing with occlusions. So if I can see something from here, if I can see this little point here, my system will currently assume that it'll see it from anywhere within a sort of hemisphere around it, which means that if I go somewhere like here where it's covered by something else, it'll expect to see that point. It'll then not see that point, and it'll think this is because there's some sort of problem. And because it wants to avoid adding bad keyframes, it will just then refuse to add anything else to the map. So this turns out to be the limiting factor to scaling right now. So things like going through doorways will be problematic. It's actually, you can go forwards. You can make quite a large map looking forwards, but then turning around and reobserving the map you've just created is problematic. So
how do you think it would work then to start a new map every time it's lost, and then sort of later evaluate whether that was a good map?
Yes, there's approaches which do that. So there was a recent paper by Eden Drummond where they do just that, and the relocalization is actually, they treat it as a loop closing event, whereby whenever tracking fails, they start the new map instantly and then splice it back onto the old map later. I'm not convinced it should be that automatic. So I actually don't mind having to press something to add a new map. Otherwise, I think this depends very much on what application you're looking at and whether you're exploring an environment or just making a little local space for you to work in.